A distance protection relay is used to detect and clear faults that occur on a transmission line. It performs this type of protection by measuring the currents and voltages, and using this, calculates the impedance of the line. If the measured impedance is less than the known impedance of the line, this indicates the line is now shorter than expected, indicating it is faulted. However, due to the inherent inaccuracies of CTs and VTs, the impedance calculations made by the distance relays cannot be guaranteed to be accurate. For example, let's assume the actual impedance of our transmission line seen here is 20 ohms. A fault now occurs just after this transmission line on the next adjacent circuit. The actual impedance from the measurement point of the D60 to this fault is 20.5 ohms. Due to the inaccuracies in the CTs and VTs, in addition to transient effects, the D60 may measure the impedance to the fault to be less than it actually is, and see the fault as being on the transmission line it is protecting. This would cause the D60 to trip the circuit breaker and shut down this transmission line when it did not need to be. Because of these inaccuracies, distance zones of protection are not set to stop right at the boundaries of the transmission line. Distance relays use multiple zones of protection, with some of them set shorter to only protect part of a transmission line, and others set longer to protect the entire length of a transmission line plus some of the next adjacent line. The zones of protection that are set to cover only part of a transmission line are said to be underreaching. The zones of protection that are set to cover more than just its own transmission line are said to be overreaching. Zones of protection can also be programmed to protect in the forward direction and the reverse direction. Zones that are set to protect in the forward direction are said to be looking into the line. Zones that are set to protect in the reverse direction are said to be looking out of the line. All protection schemes used in distance relaying fit into one of two categories: pilot-aided schemes and non-pilot-aided schemes. The distance relays used in pilot-aided schemes communicate with each other to determine whether the fault is located on the transmission line or not. The relays in non-pilot-aided schemes do not communicate with each other and instead use delays and other forms of coordination to determine whether the fault is located on the transmission line or not. All coordination in these schemes is done within each individual relay. In the category of non-pilot-aided distance protection schemes, there are two main types that we will discuss: the stepped distance protection scheme and the Zone 1 extension protection scheme. We will first describe the stepped distance scheme, which is the basic structure for all other distance schemes, so it is important to cover it in great detail. This scheme uses 4 different zones of protection to protect its own transmission line, and to provide backup distance relaying to protect transmission lines that are located next to it. We will now describe how the 4 zones of protection are set and used. The main transmission line we will be protecting will be line number 1 with the D60 located at the far left of that transmission line. The first zone of protection is set to underreaching and extends from the beginning of the transmission line to 80 or 90% of the length of the entire line. This zone is also set to have no time delay. Therefore, if a fault occurs in this zone, the D60 can be sure that the fault is located on its transmission line and can trip immediately. Zone number 1 will not protect the last 10 to 20% of the line. This area is known as the end zone. Any faults that occur in the end zone will not be seen by zone number 1 and will have to be cleared by one of the other zones of protection. The second zone of protection is set to overreach and extends from the beginning of the transmission line past the end of the line into the next adjoining transmission line. Zone 2 is usually set to 120% of the impedance of the transmission line. Zone 2 is set in this manner so that it can detect faults occurring in the end zone area that zone number 1 cannot detect. Zone 2 is also always programmed to have a time delay set between 250 milliseconds and 400 milliseconds. Using all of the characteristics we have just discussed, Zone 1 and Zone 2 have the ability to protect the entire length of the transmission line in the following way. Any faults that occur at the beginning of the transmission line will be picked up by both Zone 1 and Zone 2, as seen by the status of their pickup flags. Since Zone 1 has no intentional time delay, its operate flag will turn on immediately. The Zone 2 operate flag will not yet turn on because it has a time delay programmed within it. The Zone 1 operate flag will then trigger the D60 to trip to clear the fault. With the fault cleared, the Zone 1 pickup and operate flags will turn off. The Zone 2 pickup flag will turn off, and the Zone 2 operate flag will stay in the off state, having never turned on. On another occasion, if a fault occurred in the end zone region of the transmission line, the two zones would act differently. The fault is not within the zone of protection number 1, therefore Zone 1 will not pick up. The fault is within the zone of protection number 2, therefore Zone 2 will pick up. After the Zone 2 time delay has expired, the Zone 2 operate flag will change to the on state and trigger the D60 to trip and clear the fault. Once the fault is cleared, both the pickup and operate flags of Zone 2 will turn off. You may be wondering what would happen if a fault occurred on the adjacent transmission line, but still within the Zone 2 area of protection. Normally, after the Zone 2 time delay expired, the D60 would trip the unfaulted transmission line. However, you have to remember that every adjacent transmission line is protected by its own distance relay. This fault would fall into the second D60's first zone of protection, and the fault would be cleared before the timer of Zone 2 in the first D60 expired. The third zone of protection is set to overreach past the end of the second adjacent transmission line. This third zone is used to act as a backup for that next adjacent transmission line in case the protection on that transmission line fails. For this reason, Zone 3 is usually set to extend to the same point as Zone number 2 of the adjacent transmission line, so a setting of 220% of the impedance of its own transmission line is often selected if Line 1 and Line 2's impedances are the same. Zone 3 must have a time delay that is longer than the operate time of Zone number 2 of the adjacent transmission line. Therefore, a time delay of 1 second is commonly used. Zone 4 is used as backup protection for a small portion of the adjacent transmission line in the reverse direction. The operation of this zone is usually time delayed to allow the first zone and second zone of that adjacent transmission line to operate first. A time delay of 750 milliseconds to 1 second is common. Once each of the 4 zones have been set, the stepped distance scheme to control the breaker on the left side of the transmission line is complete. However, the breaker on both ends of the transmission line must be opened to completely clear a fault. Therefore, another distance relay must be located on the right end of the transmission line to control that breaker. The relay on the right needs to be programmed with the same characteristics as the relay on the left. However, this one will be set up to be protecting in the opposite direction. Now the zones of protection on the relay at each end will detect any faults that occur on our protected transmission line. These relays will then proceed to open the breaker and clear the fault from their own respective end of the line. The other type of non-pilot aided scheme we will discuss is the Zone 1 extension scheme. The Zone 1 extension scheme is an enhancement to the stepped distance scheme covered in the previous section. This protection scheme operates on the principle that most transmission line faults are transient in nature, which means the fault is not permanent. For example, the most common cause of faults on transmission lines is lightning. If lightning strikes a transmission line, it ionizes the air, which reduces the resistance between the different phases of the line. This reduced resistance allows for a path for current to flow and hence creates a fault. Once the transmission line is tripped and the fault is cleared, the ionized air is removed and there no longer exists a path for current to flow. Closing the transmission line circuit breaker at this point would re-energize the line and transmission of power could resume. As mentioned before, the Zone 1 extension scheme is like the stepped distance scheme in that it has 4 zones of protection. The difference between the two schemes is that in the Zone 1 extension scheme, an additional Zone 1 impedance setting is set higher to overreach into the adjacent transmission line. The impedance of this extended Zone 1, which is labeled Z1X, is usually set to the same impedance as the Zone 2 setting of 120% of the impedance of the entire transmission line. This extended Zone 1 is used by the D60 until it detects a fault within this zone of protection. Once a fault is detected, the D60 will immediately trip the transmission line since there is no delay in the operation of the extended Zone 1 element. As you can see, the D60 will trip the line even though a fault may exist in the area located in the extended Zone 1 area of protection, but be in the adjacent transmission line. When the breaker is opened and the fault is cleared, the relay will automatically reclose the breaker and re-energize the transmission line. With the line reclosed, the D60 will use the standard Zone 1 characteristic and underreach to only protect an area within its own transmission line. If the fault that occurred was a permanent fault and located within the transmission line's newly shortened zone, the D60 will trip and again open the circuit breaker to clear the fault. If the fault was transient in nature, the first occurrence of tripping the line would have removed the fault and transmission of power would resume. If the fault was permanent and reappeared after the reclosing, but was not located in the new shortened Zone 1 protected area, the D60 would not pick this up for a second time in Zone 1 and not trip to try to clear the fault. If the fault fell inside the transmission line's end zone area, the permanent fault would then be cleared by the Zone 2 protection after the set time delay. If the permanent fault were picked up by the D60's Zone 2 because it was located at the beginning of the next adjoining transmission line, the relay protecting that transmission line would pick it up in its Zone 1 area of protection and clear the fault. The D60 will then continue to use the shortened Zone 1 area of protection until the auto recloser sequence has expired. At that point, it will revert to the extended Zone 1 area of protection. All transmission line distance protection schemes that fit into the category of pilot-aided schemes are based on the basic concept of stepped distance protection. On a stepped distance scheme, any fault that occurs in the midpoint of a transmission line and therefore fits into each relay's Zone 1 will be cleared instantly by the relay located at each end of the line. If the fault, however, is located in one of the end zones of the transmission line, which is also known as a close-in fault, it will not be cleared instantly at both ends of the transmission line. The fault will be cleared instantly by Zone 1 of the relay that is located near the fault, but will not be cleared instantly by the relay at the far end of the line because the fault did not fall in its Zone 1. The fault will not be cleared at the far end of the transmission line until the time delay in Zone 2 of that relay has expired. You will remember that the delay time for Zone 2 operation is usually in the range of 250 to 400 milliseconds. The main reason to modify and improve upon the stepped distance scheme using pilot-aided schemes is to speed up the performance of clearing faults that occur in this end zone of the transmission line. Pilot schemes speed up the clearing of faults that occur on transmission lines and inside Zone 2 of the local relay by communicating with the relay at the remote end of the line to determine if the fault is actually on the transmission line. Therefore, all pilot-aided schemes require a communication channel be provided between the two relays. Over this communication channel, the two relays share information regarding the general location of the fault, allowing the clearing of faults on the transmission line to occur as fast as possible. The most common pilot-aided schemes are the DUTT scheme, which stands for Direct Underreaching Transfer Trip, the PUTT scheme, which stands for Permissive Underreaching Transfer Trip, the POTT scheme, which stands for Permissive Overreaching Transfer Trip, the Hybrid POTT scheme, which stands for the Hybrid Permissive Overreaching Transfer Trip, and the Directional Blocking scheme. We will discuss all of these schemes in the following sections. A fault that occurs in the end zone of a transmission line will normally not be fully cleared until the time delay of the Zone 2 protection element has expired. The DUTT scheme, which stands for the Direct Underreaching Transfer Trip scheme, is used to reduce the amount of time needed to wait before clearing a fault that occurs in this end zone of the transmission line. As for all pilot-aided schemes, there must be a communication channel set up between the D60s at each end of the line. This communication channel can be one of many different configurations. It can have the ability to only send one bit of data back and forth between the relays, such as a power line carrier can, or may be able to send multiple pieces of data back and forth between the two relays as fiber optic or microwave links have the ability to do. Each of the D60s must also have all of its 4 zones of protection set up to operate as a standard step distance application. For the examples we will be using in this section, we will label the 2 D60s that are protecting the transmission line in the following way. The D60 that is located on the left side of the transmission line will be called the local relay. The D60 that is located on the right side of the transmission line will be called the remote relay. As we saw in the stepped distance scheme when using the DUTT scheme, faults that occur in the middle of the transmission line, or both zones 1 of the local and remote relays, will still trip as normal and clear instantly at both ends of the line. Faults that occur in the local D60's end zone of the transmission line will be cleared at the remote end of the line instantly by the Zone 1 element of the remote relay. The breaker at the local end of the line would normally not trip until the timer of Zone 2 had expired. Using the DUTT scheme, if a fault occurred in the transmission line end zone, the remote D60 that identified the fault in its Zone 1 will immediately trip the breaker on its side of the line. Upon detecting this fault in its Zone 1, the remote D60 will also immediately send a signal, which is known as a key, over the communication channel to the local relay located at the other end of the line. This is where the term underreaching came from, because the keying signal is initiated by identifying a fault within the relay's underreaching Zone 1. As soon as the local relay receives the DUTT key from the remote relay, it will immediately trip its breaker, thus totally clearing the fault on the transmission line. The important thing to note with this scheme is that the local relay will trip as soon as it gets a transfer trip signal from the remote relay, without having to have any indication of a fault within its own zones of protection, hence the term direct transfer trip. In conjunction with the phase selector feature we described earlier, the D60 distance elements can determine which phases of the transmission line are faulted. Therefore, the D60 has the ability, through the communication key signals, to let the local D60 know which phases are actually faulted. If the breakers used on the transmission line have the ability to control each phase individually, the D60 can trigger the breaker to open only the one faulted phase. The DUTT scheme in the D60 handles this signaling of which phase is faulted by having the ability of sending up to 4 different DUTT keys that are available in the relay. Therefore, in order to fully utilize this feature, you would need to have a communication channel between the relays that can share more than one bit of information. If the communication channel you are using can only send and receive one piece of information, such as a power line carrier can, which phase of the transmission line is faulted cannot be sent, and all 3 phases of the transmission line must be tripped on all fault occurrences. The DUTT scheme has 4 flags available that are used to send a message to the other relay that indicates one or more phases of the transmission line are faulted. These 4 flags, or keys, are called the DUTT-TX1, DUTT-TX2, DUTT-TX3, and DUTT-TX4, with the TX standing for transmit bit. The D60 can be programmed to use these 4 flags in different ways to match the type of communication channel that is available, and whether or not single-phase tripping will be used. If only one bit of information can be sent back and forth on the communication channel between the 2 D60s, as in the case of a power line carrier, or when 3-phase tripping will occur for all faults, the D60 needs to be programmed to only use one of the DUTT transmit bits. When the D60 is configured to use only one DUTT transmit bit, any fault that is located in its Zone 1 of protection will turn the DUTT transmit bit 1 flag to on, regardless of if the fault is a single-phase or a multi-phase fault. This DUTT transmit bit 1 flag now needs to be assigned to an output of the D60 so it can send this transfer trip over the communication channel to the local relay. The D60 output can be a contact output that would be wired to a communication device to be sent a signal via a power line carrier to the local relay. The D60 output could also be a remote output that would send the signal to the local relay through a fiber optic communications network. A third option is a direct output that would send the signal to the local relay through a direct fiber optic connection between the 2 D60s. If more than one bit of information can be sent back and forth over the communication channel, and single-phase tripping of single-phase to ground faults is to be achieved, the D60 needs to be programmed to only use either the 2 DUTT transmit bit scheme or the 4 DUTT bit transmit scheme. If these multi-bit schemes are used, when the D60 detects a fault located in its Zone 1, it selectively turns on a sequence of bits that signal which phases are faulted. Each of these DUTT transmit bits now needs to be assigned to an output of the D60 to send these transfer trip signals to the communication channel and, finally, the local relay. The local relay must also be programmed correctly to receive these transfer trip messages. The DUTT scheme also has 4 flags available that indicate a trip message has been received from the remote relay. These 4 flags, or keys, are the DUTT RX1, DUTT-RX2, DUTT-RX3, and DUTT-RX4, with the RX standing for receive bit. Just like the transmit bit, the local relay needs to be configured to match the number of bits of data that are being sent by the remote relay. If only one bit of information can be sent back and forth on the communication channel, the D60 needs to be programmed to only use one of the DUTT receive bits. When the D60 is configured to use only one DUTT receive bit, any time that DUTT receive bit is forced on by the remote relay, the D60 will trip all three phases. The receive bit must also be programmed so that it can identify how and where the communication channel is getting input into the relay. For example, if the communication channel being used were a power line carrier, the output of the PLC hardware would be wired to a contact input of the D60. This contact input needs to be assigned to the DUTT receive bit. If the communication channel were from a direct fiber optic connection between the two D60s, the input to the relay would be a direct input. This direct input would then need to be assigned to the DUTT receive bit. If more than one bit of information can be sent back and forth over the communication channel, and single-phase tripping of single-phase to ground faults is to be achieved, the D60 needs to be programmed to only use either the 2 DUTT receive bit scheme or the 4 DUTT receive bit scheme. Please note that both the local and the remote relay must be programmed with the same number of corresponding transmit and receive bits. Each receive bit will then have a different input assigned to it, each of which comes from the communication channel. The DUTT scheme in the D60 has some output flags that are set based on the status of the DUTT receive keys. The name of these output flags and the reason they are turned on are as follows. The DUTT operate flag will turn on when the local D60 receives a signal through the DUTT keys that at least one of the phases of the transmission line is faulted. This output flag should only be used to signal the breaker to trip if three-phase tripping is always required. The D60 has a DUTT trip flag for each of the three phases of the power system. For instance, the DUTT trip A flag will turn on when the local D60 receives a signal through the DUTT keys that only phase A is faulted. This output flag should be used to signal the breaker to trip only phase A if single-pole tripping is possible. The same is true for phase B and also for phase C. The DUTT trip 3P flag will turn on when the local D60 receives a signal through the DUTT keys that there is a multi-phase fault on the transmission line. This output flag should be used to signal the breaker to trip all three phases of the transmission line. We will now go over the following settings that need to be configured to have the DUTT scheme operate correctly. Before the DUTT scheme can be used in the relay, it must first be enabled in the function field. When the trip output flags of the DUTT scheme that were described earlier are forced on by the remote D60 through the communication channel, they are then used to signal the breaker to trip. These signals need to be made to stay in the on state long enough for the breaker to complete the tripping process. Entering a delay in the CLIN delay field shown here will ensure that the DUTT trip output flag stays in the on state long enough for the breaker to fully open. The next field to set is the number of communication bits that will be used by the DUTT scheme as we described earlier. The options to choose from in this field are a 1-bit, 2-bit, and 4-bit communication schemes. All that is required from the user is to select the number of bits to use and then connect the DUTT transmit bits to the communication channel. The D60 will take care of turning on the correct bits when each type of single-phase or multi-phase fault occurs. The next 4 inputs in the menu let the D60 know which inputs to the relay are the 4 DUTT receive key signals. Again, these may be contact inputs, remote inputs, or direct inputs. If only one key is being used in the DUTT scheme, only the field labeled RX1 needs to be assigned. If 2 keys are being used in the DUTT scheme, only the fields labeled RX1 and RX2 need to be assigned. If all 4 keys are being used in the DUTT scheme, all 4 receive bit fields need to be assigned. Finally, set the target and the event fields if you want the operating of the DUTT scheme to show up on the front panel and in the event record. The PUTT pilot-aided scheme stands for the Permissive Underreaching Transfer Trip Scheme. And just like the DUTT scheme, The PUTT scheme is used to speed up the clearing of faults that occur in the end zone of a transmission line. As for all pilot-aided schemes, a communication channel must be provided between the two relays located at each end of the transmission line. The PUTT scheme works by having the remote D60 send a PUTT key signal to the local relay whenever it detects that a fault has occurred within its underreaching Zone 1 area of protection. This is where the expression underreaching comes from in the term permissive underreaching transfer trip. The difference between the DUTT scheme and the PUTT scheme is what the local relay does when it receives the key signal from the remote relay. You will recall that in the DUTT scheme, the local relay would trip as soon as it received the key signal from the remote relay. In the PUTT scheme, the local D60 PUTT logic will now only trip the breaker if it gets the PUTT key and the local relay has detected a fault within its Zone 2 area of protection. If the local D60 received the PUTT key and it does not detect a fault within its Zone 2 area of protection, the PUTT scheme will not cause the local D60 to trip. Just like in the DUTT scheme, in conjunction with the phase selector feature, the PUTT scheme can determine which phases of the transmission line are faulted. Therefore, the D60 has the ability, through the communication key signals, to let the local D60 know which phases are actually faulted. If the breakers used on the transmission line have the ability to control each phase individually, the D60 can trigger the breaker to open only the one faulted phase. As in the DUTT scheme, the PUTT scheme handles this signaling of which phase is faulted by having the ability of sending up to 4 different PUTT keys that are available in the relay. These keys are called the PUTT TX1, PUTT TX2, PUTT TX3, and PUTT TX4. Again, in order to fully utilize this feature, you would need to have a communication channel between the relays that can share more than one bit of information. If only one bit of information can be sent over the communication channel, or 3-phase tripping will be used for all faults, the D60 needs to be programmed to only use one of the PUTT transmit bits. Therefore, the sending of this one PUTT transmit key will give permission to the local relay to trip all 3 phases if it detects a fault in its zone number 2. If more than one bit of information can be sent back and forth over the communication channel, and single-phase tripping of single-phase to ground faults is to be achieved, the D60 needs to be programmed to use either the 2 PUTT transmit bit scheme or the 4 PUTT bit transmit scheme. Again, like the DUTT scheme for these multi-bit formats, when the D60 PUTT scheme detects a fault located in its Zone 1, it selectively turns on a sequence of bits to send over the communication channel and signal which phases are faulted. Like the DUTT scheme, the local D60 needs to be programmed to let it know how many PUTT keys it will be receiving. If one PUTT key is selected, the relay needs to be programmed to let the D60 know what input is being used as the PUTT key. Once this single PUTT receive signal is detected to be on, the PUTT scheme will trigger the D60 to trip all 3 phases if it detects a fault in its Zone 2 of protection. If multiple keys are used, the D60 needs to be programmed to let it know which relay inputs are being used as the PUTT key signals. Once this is done, if the local D60 detects that a sequence of keys has turned on, only the phases indicated by that key sequence will be given permission to trip if a fault is detected in Zone 2 of the local relay. All other phases that have not been given permission will not be triggered to trip by the PUTT scheme. The PUTT scheme in the D60 has some output flags that are set based on the receiving of the permission keys from the remote relay and detecting a fault within the local relay's Zone 2 of protection. The name of these output flags and the reason they are turned on are as follows. The PUTT operate flag will turn on when the local D60 receives a signal through the PUTT keys that at least one of the phases of the transmission line are faulted, and the local relay has also detected a fault on that same phase in its Zone 2. This output flag should be used to signal the breaker to trip, as 3-phase tripping is always required. The D60 has a PUTT trip flag for each of the 3 phases of the power system. For instance, the PUTT trip A flag will turn on when the local D60 receives a signal through the PUTT keys that phase A is faulted, and the local relay also detected a fault on phase A in its own zone 2. This output flag should be used to signal the breaker to trip only phase A if single pole tripping is possible. The same is true for phase B and also for phase C. The PUTT trip 3P flag will turn on when the local D60 receives a signal through the PUTT keys that there are multiple phases detected in the fault as seen by the remote relay, and the local relay also detected a fault on multiple phases in its own zone number 2. This output flag should be used to signal the breaker to trip all 3 phases of the transmission line. We will now go over the following settings that need to be configured to have the PUTT scheme operate correctly. As for all schemes, before the PUTT scheme can be used in the relay, it must first be enabled in the function field. The RX pickup delay field is used to cope with false signals that may be received over power line carrier communication channels. Adding a delay to this field means the PUTT scheme will not accept the PUTT receive signals as being on until the signal has been in this state for a period longer than the RX pickup delay. Setting a delay here will increase the overall response time of the scheme. This delay should be set longer than the longest false signal that can be received simultaneously with the Zone 1 pickup. As in the DUTT scheme, setting the seal-in delay will cause the D60 to keep the trip output signals in the on state for a minimum period of time as specified here. This allows the trip signal to be present long enough to allow the breaker to complete tripping. The next field to set is the number of communication bits that will be used by the PUTT scheme as we described earlier. The options to choose in this field are to use a 1-bit, 2-bit, and 4-bit communication scheme. The next 4 inputs let the D60 know which inputs to the relay are the 4 PUTT receive key signals. Again, these inputs may be contact inputs, remote inputs, or direct inputs.